Today's presentation is going to be focused on proposing an alternate method for landscape controller testing. And Mark Crookston will be the main presenter, who's a semi-retired water engineer from Northern Water. He's got lots of experience in the industry and worked with Northern Water since 1986. He's involved in many professional organizations such as the Irrigation Association, ASABE, USCID, and contains many certifications, as you can see there on the screen, within the irrigation space. Our other presenter today is going to be Brent Meekum, who is a retired industry development director from the Irrigation Association, who also worked for Northern Water. And just like Mark, he has several certifications and lots of irrigation experience. And so today, I'm going to turn it over to them and let them begin their presentation about an experiment that occurred over the last 2 years at the Irrigation Innovation Consortium headquarters located here in Fort Collins, Colorado. So without further ado, Mark, would you take over?
Very good. I wanted to point out that Brad has been working on updating the SWOT testing protocol for multiple years. And the Irrigation Association partnered with ASABE towards making an ANSI standard, national standard, and hence ASABE X627. And we'll have Brent talk more about the progress there towards the end. As I go through the slide presentations, we're going to hold questions till the end, but if you would take note of what slide you want to reference, that will help me get on board quicker about what really raised a concern or a question or some comment or input, and that would be very helpful. We've got about 80 slides to go through, and it's very data intensive, so I think we better get started. The current version of ASABE X627 includes both the original 2008 testing protocol, now referred to as test method number 1. It was created by the Irrigation Association Smart Water Application Technologies, or SWAT committee, along with now a proposed new alternative test method number 2. Test method number 2 was utilized in this 2019 testing of the Irrigation Innovation Consortium, whereas test method 1 is the original one utilized by EPA in their water sense certification. So, but significant advancements in irrigation controllers have been made in the last decade, supporting improved irrigation management, water conservation. To recognize this progress and encourage additional development, an alternate testing protocol has been developed. This alternate test method places renewed emphasis on deep and infrequent irrigation to take greater advantage of rainfall and better support low water use plantings. Now, the controller testing equipment was moved from Berthoud to Fort Collins, and when that was done, the capacity for testing was increased to a total of 24 controllers, each having 6 zones or stations. The alternate testing protocol increases the testing period from 30 days to 90 days and is consequently a more rigorous test. As the purpose of the 2019 testing was principally for validation of the alternative test method, it included replicates of each controller. Usable data was successfully obtained from 22 of those 24 controllers. 8 controllers used on-site weather sensors, while 14 controllers utilized Wi-Fi internet for weather data sources. All controllers tested had already achieved the WaterSense label. Replicates of the Wi-Fi controllers of the same make and model were programmed for different virtual locations in northeastern Colorado. So we've tried to make the testing as defensible as we could and to learn as much as we could from what was going to be accomplished. Each controller make and model was given a test ID ranging from A to J. When comparing controller performance, the results from available replicates were averaged. 4 of the controllers utilized the wireless sensors, which were installed at the consortium. And 6 of the controllers utilized Wi-Fi internet. And essentially, those controllers could be located anywhere and obtain their data for a designated location from a weather station or a network there, and the testing could be successful. Now, this photo shows the setup of the equipment that was utilized in 2019. The large test board back in center holds 16 controllers, and the smaller test board to the right holds 8 controllers. The output wiring from each controller was connected to Phoenix contact relay switches that were in turn connected to a 16-port Campbell Scientific I/O module, and then to either a CR1000 for the large test board or a CR800 Campbell Scientific data logger on the small test board. Both data loggers were equipped with cellular modems, and the Wi-Fi irrigation controllers were provided connectivity via a T-Mobile hotspot that was in the same building. So the required reference ET that you need to do this testing was all obtained from 3 regional weather stations. 2 of the stations were part of the Northern Weather Network in northeastern Colorado. The 3rd station was a new install that we did at the consortium in Fort Collins. 15-minute weather data was validated through a QA/QC process and then aggregated into hourly data. The X627 protocol uses an hourly time step. The hourly data was then processed through RefET version 4.1 to provide a reference ETO. And the only of the 3 weather stations that had a weighing bucket was the one at Berthoud. And that kind of device typically has some bounce in its readings. And so it was post-processed to remove that signal bounce that's so common. And then its data was essentially mimicking the discrete rainfall events of a 0.005 inch tip rain counter. So this is the Fort Collins East Weather Station at the consortium. It used a ClimaView 50 from Campbell Scientific. It was provided to need the reference data for the controllers that were utilizing on-site sensors. It's very compact. It has no moving parts, so there's very low maintenance or service requirement. Yet it provides weather parameters and accuracy very comparable to more traditional ET networks. With no gill shield, the temperature sensor benefits from onboard corrections utilizing wind speed and solar radiation. Similarly, the drip counter rain gauge has onboard compensation for high rainfall rates, which are typically undermeasured by traditional tipping bucket rain gauges. And it proved its mettle in 2019 with one very high rainfall event. This weather station is the Berthoud Weather Station at the Northern Water headquarters. And again, it has in fact, you can see the tipping bucket in the background there, the weighing bucket in the background that we utilized for that weather data. This is Roland Moore Park Weather Station. It's in the park owned by the city of Fort Collins. The weather station itself is attached to the scoreboard on one of the ball fields. You can see the foul line there next to it. But the anemometer, the tipping bucket, the air temperature, and solar radiation are all nestled in there together. It's only experienced damage from a home run one time. So far, not too bad. Now the parameters of the 6 virtual landscapes used in the testing protocol, number 2, are intentionally varied to provide a good range of values. You would never expect to see this much diversity in one landscape, but for reasons of testing, we wanted to cover the range as best we could. Plant factors vary from 0.81 for cool season turfgrass down to 0.30 for native shrubs. These stipulated plant factors already incorporate all adjustments for plant species density, microclimate, and managed stress. Plant root zones vary from 6.5 inches up to 20 inches. Now these are the soil parameters for the 6 virtual zones. They varied intentionally over quite a range, from loamy sand to clay. However, the values for available soil water capacity, allowable depletion, basic soil intake rate, surface slope, and temporary surface accumulation of rainfall and irrigation were all distinctly declared to avoid ambiguity so that everybody was playing with the same numbers and trying to target the same performance. The parameters of the 6 virtual irrigation systems were also intentionally varied. 2 of the zones utilized drip irrigation. The maximum and the other 4 utilized 2 were pop-up, 3 were pop-up, and 1 was rotors. The maximum irrigation cycle on time was also specified, as is its corresponding minimum required soak interval. And runoff from hourly rainfall events was calculated the same as for sprinkler irrigation events. So they were treated equitably. And we could do that because of the hourly time step. Now, the principal objective of the 2019 testing was validation of the test method number 2, hence replicates. Provided increased defensibility and verified the consistent functionality of the same make and model controllers. Use of 3 different weather stations verified the close agreement of calculated reference ET regionally in the northern Colorado area. Rainfall was likewise similar in quantity, but varied in the day-to-day occurrence as storms moved through. The 2008 testing protocol, test method number 1, did not include evaluation of irrigation interval or frequency, whereas irrigation interval is included in alternative test method or protocol number 2. Consequently, each zone was configured to water deeply and infrequently as appropriate within the functional constraints of the given controller. Plant soil and irrigation parameters were specified directly whenever possible, and advanced operational features of each controller were utilized as appropriate. However, scheduling options that utilize forecasted or predicted rain were typically minimized in the testing. Past testing experience has shown such predictions for northeastern Colorado can become a significant pitfall, resulting in poor controller performance. Evaluating the advantages and disadvantages of such features was deemed more appropriate for later testing. So now, some of the immediate questions that have come up is which zones had the longest irrigation intervals? Zones 4 and 5 had 10 days and 12 days respectively. And this is unusual for management of many landscapes, but it's becoming more and more common. So for controllers that utilize days of week scheduling, where each zone must be scheduled to water at least once a week, some scheduling compromises were required. And there'll be some information about how that affected the poor performance between one type of controller and the other. But those are long intervals. Low water use plantings, such as native shrubs, thrive best when watering is deep and infrequent, potentially only as infrequent as once a month. This capability will become increasingly important as more landscapes incorporate low water use plants. Without it, the full conservation potential of such landscapes may not be realized. And watering such landscapes like the native shrubs can often can cause the landscape plantings to deteriorate because they simply aren't happy when they're kept too long at full capacity. They like to dry down, and in order to maintain plant vigor and health. By the resulting test numbers, some zones proved more difficult than others. Zone 2 and 6 were the most challenging to schedule appropriately by the controllers we tested. Surprisingly, both were the warm season turf grasses with relatively shallow root zones on clay soils and steep surface slopes. So normally we don't think turf is too tough to schedule, but when you throw in the heavy soils and the steep slopes, there's a lot of cycle and soak going on. Now we want to talk about some test results. We're going to look first at the zones for the controllers, and then we'll look at the controllers themselves. Following graphs will present average performance by categories for the 10 controller makes and models, using their assigned IDs of A, B, C through IJ. This controller performance graph for zone number 1 includes both irrigation adequacy and irrigation scheduling efficiency. And irrigation adequacy is, did it water enough that the plant was not seriously stressed? And irrigation scheduling efficiency is, it watered just enough. So if it waters too much and water is unneeded, then that would lower that efficiency. But they work together. A brief summary of zone number 1 is included in the upper right-hand corner. So you can kind of see what kind of zone this was as you look at that. And you can also see that the difficulty rating of the zone was 4. So it was a difficult, not the most difficult, but it was difficult. The higher dark dashed line is the reference value for irrigation adequacy for test protocol, from test protocol number 1, while the lower lighter dashed line is the corresponding reference for irrigation scheduling efficiency. Underwatering will typically increase irrigation scheduling efficiency, but decreases irrigation adequacy. Conversely, overwatering typically increases irrigation adequacy, but decreases irrigation scheduling efficiency. For zone 1, controller H had high marks for both, with several others following closely, whereas controllers D, I, and J tested poorly in 2019, whether in part or in full, due to some suspected factors, and I'll bring those up before we get too much farther. This is a controller performance graph, again, of irrigation adequacy and irrigation scheduling efficiency, but for zone number 2. This was high difficulty, a rating of 5. Controller C, again, had high marks for both, with several others following closely, whereas controllers D, H, and J tested poorly. And there may be reasons why they did. So this is now zone number 3. Again, irrigation adequacy and irrigation scheduling efficiency. And we're seeing more controllers do well. C, E, F, G, and H had relatively high marks, whereas controllers A, B, D, and I, and J tested poorly in one or the other or both. This is for zone number 4. It's of a low difficulty, only 2. Controllers B, D, E, F, and H had relatively high marks for both, whereas controllers A, C, I, and J tested lower in irrigation adequacy in 2019. And controller performance now for zone number 5. It was the lowest difficulty. You would assume that every controller would do well on the easiest zone. But again, there was some issues going on with some of the controllers, potentially for various issues. But controllers B, C, D, E, F, G had relatively high marks for both categories, whereas controller A, I, and J were lower. Now this is zone number 6. It was the highest difficulty. Controllers C, F, and G had relatively high marks for both areas, whereas controllers A, B, D, H, and J tested lower. So there is, what we're pointing out is that there's some radical differences in how all these controllers performed, whereas remember that all of them had already passed the EPA WaterSense, had achieved the EPA WaterSense label. But that only requires a 30-day test. And so a longer test is obviously showing to be more difficult, more demanding. Now we want to look at the average of 6 stones for each controller and look to see how that compares. What did we reference, or what standards did we look at to rate how they were doing? Again, irrigation adequacy greater than 80%, scheduling efficiency greater than 90, irrigation adequacy and scheduling efficiency averaged, we left that at 80%. Then we introduced a low irrigation frequency, a ratio to the optimum irrigation interval. We're hoping that it would be less than 2. And then we looked at having high effective rainfalls, close as we can to the measured rainfall. And we looked at not having excess net irrigation so that we would have some compromises there. So this is for the average of irrigation adequacy. And you can see right off the bat that 4 controllers surpassed that threshold or comparison threshold. The current target is that horizontal dashed line, and controllers C, E, F, G all performed well. Now this is irrigation scheduling efficiency. The threshold from protocol number 1 is higher at 90%, and you can see that only 1 controller got that high, but there are several that are in the ballpark. One of the things I want to point out is that controllers A, B, and H, turns out that these readings for them are elevated because of their low irrigation adequacies. Unless essentially they let the root zone dry down, there's plenty of room to capture whatever irrigation was thrown at them. So this is part of that. Irrigation scheduling efficiency doesn't tell the whole story, and neither does irrigation adequacy. So by combining the two, having both irrigation adequacy and scheduling efficiency averaged together, and having a reference threshold of 80, you can start to see that there were clearly 3 controllers that were able to meet that, averaging on all zones across. 1 that was a close follower, but you also see that there are some others that for various reasons did not do well in 2019. And this is where you may want to start taking some notes as to which controllers you look at and would place emphasis on on their performance and the things that they do that you like. So this is a graph of irrigation frequency as a ratio of the optimum irrigation frequency. It's an average across all zones. Controllers A, D, E, F, and G performed well. They were all at or below the target 2-point factor. Controller C, although it performed very well in most other categories, notice that it's irrigating 4.4 times the optimum. And it's constrained because it requires weekly scheduling of irrigations. And it also only has 3 scheduling programs in the controller to work with for all 6 zones. So this will prove interesting later on because it did perform well in all other categories, but this one was one that would be totally missed in the test protocol number 1. So this graph of effective rainfall presents the average across all zones of each controller make and model. The 2 horizontal dashed lines are the highest measured rainfall of the 3 weather stations and the lowest measured rainfall of the 3 weather stations that we used. Controllers B, D, E, and F performed well. And that's kind of amazing. I believe that they averaged close to 80% effective rain. Elevated ratios from controllers I and J would appear to be indicative of under irrigation or not watering enough. And because their irrigation adequacies were 49% and 12% respectively. So they had plenty of room to capture rainfall in their root zone. So those 2.2, getting above that kind of indicates that is not what we want. Getting down there below 2 starts telling us that maybe the threshold should be 1.8, but that's for someone else to decide what those performance agendas would be. This graph is net irrigation direct runoff plus soak runoff. It is the average across all 6 zones for each controller make and model. Theoretically, they should all be close to 0, and we have controllers that did very well there. Because this kind of runoff and soak runoff, they're the consequence of excessive cycle on times and or deficient soak times. And elevated values for controllers D, I, and J resulted from sporadic episodes and were not consistent poor performance throughout the test period. So it wasn't that they did bad all the time. It was just on specific events that they seemed to just lose their brain. And it was significant enough that it affected the results notably. No solid explanations can be offered about what happened here, but we do have a couple of clues that could be considered. One is that controller D used on-site sensors, wireless sensors, and if connection between the controller and the sensors is sporadic, that could possibly contribute to this kind of performance. The weather service for controller I, that company has its own weather server to provide rain and ETO to its controllers. That controller changed companies, and in that transition, the weather server was allowed to go offline towards the end of the testing period. And normally, I would have expected controller I to do much better, but without good rainfall and weather data, it had to rely totally on historic averages. And then controller J, the only thing I can offer on that is that I would program in all the parameters for what I wanted it to do, and then when I went back to check it, they would not stick. Some of them would, only some, but some would unilaterally change back to defaults rather than stick with what I asked it to do. And that could be an issue on J. But the rest of the controllers actually did pretty well. And it should be noted that A, B, C, and D are all using on-site sensors. So again, C did very well, D struggled, and even though they did not have direct runoff and soak runoff problems, there were other issues with controllers A, B, C. Now this is a graph of excess net irrigation, of overwatering. It's an average across all zones. Cycle soak runoff along with excessive deep percolation are included in excess net irrigation. All controllers performed more or less acceptably in 2019 except controllers G and J. Now the utility of alternative test protocol number 2. It provides a longer test period, yes, and it evaluates more parameters than are required in test protocol number 1. But the water sense label that all 22 controllers had means that they're capable of meeting performance targets over a 30-day period. And as I reviewed the soil moisture balance graphs from the 2019 testing, it was clear that the controllers had multiple zones with 30-day periods where irrigation adequacy and efficiency expectations could be met. However, the more rigorous 90 days indicated that it doesn't always hold over long time periods, and rainfall is one of the things it has to account for. Also, the falling ET during a beginning of the season or end of season is another place where a controller that doesn't adapt to that or doesn't detect that will get off and not perform as well. And a shorter 30-day period allows it to be right dead center in the middle of the summer when everything is basically flat and consistent. So the test results of the 2 well-performing controllers, and these are going to be individual controllers. The first one is number 6. The second one will be number 14. These performed well, and so it's important to kind of see, well, the controllers that did well, what did they do that helped them perform well within these testing parameters? So this is a copy of the summary report that is produced from when all the data is processed. The pink shaded boxes down here automatically highlight when they're outside of the parameters that test protocol number 1 wants to see. And so there are some key things in there, but notice that not everything over 90 days stays stable enough for what test protocol number 1 wants to see. The pink boxes indicate that parameters not fully meeting possible performance thresholds, but so far no performance thresholds have been set for test protocol number 2. The 90-day period is having a big effect. These results, though, could be considered indicative of the better performing smart irrigation controllers currently available in the irrigation industry. So by having 2 to 4 controllers that perform decently and well, that provides some basis for starting parameters for evaluation of test being used in test protocol number 2. We know what some good controllers can do, and we can say, well, is this reasonable, and should we expect other controllers to be compared against that? Although some parameter values may appear a bit low to those familiar with test protocol number 1, they do represent a 90-day test period, not a 30-day test. And the circled red value of 83.8 is actually the average of the irrigation adequacy and irrigation scheduling efficiency across all zones. It provides a quick one-number comparison of one controller performance to another. And so you can see that controller number 6 had an average of 83.8 across all zones during a 90-day period. So for each virtual zone, the gray bar represents gross irrigation by a non-smart controller through that 90-day period. So this would be a non-smart controller would be one that is typically fired up in the spring and programmed to water well in July and August, and then it's not touched again until it's shut off in the fall. So this is non-smart. It's not reacting to the weather or to rainfall. It's simply what a big chunk of controllers installed throughout the United States actually do. The blue bar is the performance of this better controller, one of these top controllers, number 6. How did it perform? And the green bar is what the optimal controller, or the pseudo controller, would do if it properly walked through the same weather data and the same zones and specifications. So you can see that there's room for improvement, both from going from a non-smart controller to a smart controller that performs well, and then going to down to even if we change landscape. So zone number 4 was the native shrubs that has a very low water requirement. So if you look at what the highest plant requirement was to the lowest plant requirement, that's the potential that could be saved from simply changing plant materials and properly irrigating. This is kind of dangerous to say that all plantings and all landscapes in northern Colorado or anywhere should be of this kind. But it does say that the relative savings that we're looking at is that there are multiple fronts where we can achieve additional water conservation and do a better job of managing irrigation. So this is again using those same kind of results. But from a non-smart controller to an optimal controller, we could save 27% of the water. And what's interesting is that typically you see marketing that will claim that if you buy our smart controller, you can save 50% of your water, without ever knowing how much water the individual landscape may currently be using. But this would say that over a broad spectrum of landscapes, that 27% is what would have been done under this testing, and is available by switching from non-smart to a smart controller. If we went from non-smart to optimal scheduling, gonna go back to optimal scheduling, we could save 48% of the water that was applied by the non-smart controller. And if we went to optimal scheduling with a high irrigation efficiency, we could save 58%. So irrigation efficiency is a big factor in conserving water. And then if you go to the low water use landscapes, there's a whopping 86% that could be reduced from a non-smart controller. So number of irrigation days. So this would highlight those controllers that are irrigating too often, rather than watering deep and infrequently. They're watering more than we want them to. Deep and infrequent irrigation encourages deeper and higher density rooting. Effective rainfall is thereby increased. It also reduces water loss to evaporation, resulting from frequent surface wetting. Also, if you judiciously manage the plant stress levels you can reduce ET even further and help maintain desired plant appearance, health, and vigor. So now another thing that's important in testing controllers is what watering window is required, because as soon as municipalities go to watering restrictions, you're constrained of which days or which hours you can water. And so this is a real quick blast of any time in an hour a zone had a minute of run time, and we total those up day by day. And you can start to see that controller number 6 was that there were zones that were typically running 7 hours. Yeah. So, but more meaningful to me is when we lump all the sprinkler zones together, because they typically are going to be required to water at night. And we lump the 2 drip zones together because often you can get an exemption to water that during the day. It actually helps the water move horizontally better. And so the green is the sprinkler watering hours, and the blue is the drip watering hours. But notice that the blue line is what our optimum would be, and the green line, and that's for drip, because it's a slow, long process of watering those zones. And the green would be the irrigation, which can happen much quicker with the higher application rates. But notice that, yes, a lot of them are right there where we wanted them, but there's several that are much more than we would hope for. So this becomes important because not all controllers will stack zones on top of one another. So when they cycle and soak, there are controllers that will do one zone at a time. They'll cycle on, cycle off, cycle on, cycle off, cycle on. It takes an incredibly long, big, large watering window to get through all that. Whereas other controllers will actually stack those zones. They'll water each zone, it's allowed run times, and it'll start over and come back and water them again until all of them have gotten the water they were supposed to. And that compresses that watering window so that you can get through the watering in a reasonable time period. And this may not be important most years, but on the years it can be a matter of actually maintaining a healthy landscape or not. So this is effective rain for controller number 6. And the dark, it's a running sum of effective rainfall zone by zone over time. The dark lines are actual effective rain, and the dashed lighter lines are for optimal scheduling. So you can see that they track each other pretty well. But I think this graph is more meaningful to me because now we're comparing the effective rain zone by zone against what the optimal irrigation would be. And so obviously having a one-to-one, following the one-to-one line is optimal. And this is a good performance by a controller that it's staying fairly close to that one-to-one and it's doing a good job. But it's also getting up there, on average, they were 81% of the measured rain was actually effective rain that was stored in the root zone. And when we get to the next controller that we're going to highlight, you'll see that it did not do this well. So this controller did much better because it watered deeply and infrequently. It did much better at capturing rainfall, whereas the other controller watered essentially every week and wasn't able to catch as much rainfall and did not do as well. So effective irrigation running sums for controller number 6. You want the dark line to approach the yellow line, and you can see that optimal is not always better than when it gets behind, but they basically should track each other. And I was very pleased to see that this controller was able to do that. Effective irrigation controller number 6. Again, we want it to follow the one-to-one line. Obviously irrigation are events, and so timing of that event is very important about whether it stays there. We want to actually see these jumps and spread out because that's watering deeply and frequently, whereas if they were always right on the line, that's watering every day. And that's not the intent of managing the landscape properly. Now, effective irrigation. These graphs compare irrigation events for zones 1 and 2 for controller number 6. The lighter bars, so you can see the pale blue and the pale pink, are for optimal scheduling, and the darker bars are the actual irrigation events. Now, there's a couple of things that you can quickly see from this kind of graph. Because when irrigation events are lower than the optimum, they have to happen more frequently. So if you count up the optimum number of events and you count up the actual, you can see that, yes, it's putting on the right amount of water, but it's irrigating more frequently. And so it puts on less. And so it has to have more irrigation events to do that. Also in the background, notice that there's a faint line, which is the reference ET. And that's there so you can see that over this 90 days, we went from some very high ET values down. And that's what the 90-day test is all about, is we give the controller a changing weather requirement that it has to chase. And a 30-day test doesn't necessarily do that. So there you can see that by going from July 15th to mid-October, that we got that seasonal drop in irrigation requirement. And you notice that this controller was watering more frequently, and then it started not watering as frequently. And that's exactly what we wanted to see. Now, this is zones 3 and 4, the same one. Again, we're looking at the same types of things. We're seeing the same kind of irrigation, just depends on how many days it waits until it has to water. And we're seeing really good correlation between the optimal and the actual, that they're happening almost as scheduled, following along very nicely. This one, the optimal would only have 3 irrigations. You can see there's several more, but they are less. And so that's a compromise in the programming or operation of the controller. These are zones 5 and 6. Again, for controller 6. Again, we're watching for that lighting up of irrigations events as we go towards the end of the season. We're looking to see how well does the actual irrigations match up with what the optimal irrigations would be. Yes, there are differences, but it's all about coming close and not wasting water. We may come back to these if there are questions or comments about those. This graph is going to walk through the zones again, and I'll move pretty quickly, but what I want to highlight is that this is daily irrigation and rain. The rain is the green bars, and the irrigation is the blue bars. And when you see dark blue, that means that that's overwatering, and that will show up down here as pink. So when you see dark blue and pink together, that indicates that there's room for improvement. So this is zones 1 and 2. The pink is the difference of net irrigation and effective irrigation. And the net irrigation is consistent during the growing season. It's essentially the same amount every time there's an irrigation. And that's what we wanted to see. When there's no dark blue visible, there should be no pink visible. And similarly with net rain, if there's a dark green visible, like there is here, that means that some of that rain was not effective. And because the light green is what was effectively stored in the root zone. So actually this provides a lot of good information about how well the controller is doing. This is control zones 3 and 4 for the same controller. Again, you can start to see that there was some, because of the change in scales for the root zone, you can see that we see the same amount of irrigation be applied, but we do see some dark blue and we see some pink. And but all in all, we're seeing those efforts to lighten up as we go to the end of the season when the ET demand goes down, and we're seeing deep and infrequent irrigation for those zones as well. This is 5 and 6. Again, the amount of net irrigation is consistent during testing. Ideally, there's no dark blue or pink. They should not be visible, nor dark green bars for rainfall. It's evident for that some irrigations were delayed because of rain, and that seasonal declining reference ET was impacting what the controller was doing. And probably the true story is seen in the readily available soil moisture balance. Readily available because field capacity is the top green dashed line. The allowable depletion or target depletion is zero moisture, zero allowed depletion. And then wilting point is the dashed red line at the bottom. Now that's a carryover from test protocol number 1 and how things were done there. But what we don't want to see is we don't want to see any of the soil moisture balances going below the target depletion level. And we would want to see the stair steps following the optimal in the light gray behind it. So, and we're seeing really good agreement on zone 1 and really good agreement on zone 2. The controller is doing what we hoped for and expected it to do as we programmed it up. Very similar here. Again, you can see when the rainfalls occurred the blue is the irrigation and the green is the rainfall, and you can see that there's a good travel down through the available moisture, and the controller is trying to do that. This one hung up a little high. This one did pretty well. We've got 5 and 6. This is interesting that when there were periods of rain that the moisture balance stayed higher at field capacity. We had to wait until the rain went away before we started getting the good declines again. But this is what we want to see. We want to see it filled up. We want to see it drawn down. We want to make room to capture rainfall. We want to keep those plants healthy and well. Now we're going to skip to controller 14. That's controller ID number C. And we'll go through kind of the same review of it. And for me, it's very fortuitous that the two controllers that performed very, very well. One was used on-site sensors. One was a Wi-Fi controller. One of them had to water frequently, essentially weekly. And one did a better job of doing days of interval and spreading out those things. And so we'll start to show some differences between what the impact of those differences are. So again, this is the summary report for controller number 14 with wireless sensors. Again, it has some pink because these are carryovers from the test protocol number 1, where they're really looking for near perfect performance in a 30-day period, and not allowing for the variations that are going to creep in when there's a 90-day period where it has to track. These are the performance parameters, a close-up of those. So if you look at the last page where this performance parameters are, this is kind of highlighted those. You can see what those are. You can see the irrigation efficiency was essentially nice and high except for one zone. Irrigation ratio. This is controller number 14 that was so high on its frequency. Notice that we're not seeing 2s or lower. We're seeing 5.1, 4.2, 3.5. Irrigation scheduling excess. Essentially nothing on 2 zones and some on others, but adequacy and efficiency, 3 of those zones are essentially perfect. So, and then it's overall irrigation adequacy and irrigation efficiency, 83.9, the top score. So again, we look at as the gray is for a non-smart controller programmed for the whole season and not adjusted or non-reactive to weather conditions. The blue is now controller number 14, and the green is the optimal controller that would water at the perfect time. So, and I put up here the difficulties. The difficulty of zone 1 was 4. 5 difficulty, zone 5 was the lowest difficulty. Zone 6 is the highest difficulty. So you can start to see that this controller actually did quite well. But there is definitely room for improvement from a non-smart controller to controller number 14. The vertical gray arrows show that there's a fair amount of savings that's potential there. If you go to the perfect, even though controller 14 did well, there are zones where you could get a significant savings. And then if you change the landscape and require less water, there would be additional savings too. So this is the amount of savings that test protocol number 2 is addressing, is how much can we save from going from a non-smart, of going from a non-smart to controller number 14. And if we can do perfect, that would then get us to this additional savings that we could get down there. So this is the potential water savings by changing from a non-smart controller. And notice that 23% could be saved from non-smart controller number 14. Again, that's not 50%. It is often claimed to get the 50% savings, which I agree can be achieved, but you're fixing additional things besides just the controller. You're fixing previous problems, or you're doing more than just changing the controller to help them get there. But there's significant savings in available as we work to even improve our smart controllers further. Potentially, we could get up to 48% with optimal scheduling. And then if we went to high irrigation efficiency, we could get another 10%. So this is what we're shooting for. And this is why we're doing testing and trying to advance test protocol number 2. This graph emphasizes the need for different zones to have different irrigation intervals or frequencies. The benefits of watering deeply and infrequently can be substantial. Controller number 14 has significantly more irrigation days than optimal for all zones because it's constrained for weekly watering with only 3 available controller programs. So this starts to show that we really need to have controllers that allow you to water every zone according to its needs, not just to how it fits into the available capabilities of a standard controller. This is the watering window. Again, this is a lot of noise, but it shows that how much the different zones had to run, or it's actually counting. If an hour had 1 minute of runtime, it would count that hour. So you start to see that zones had 5 hours or 3 hours or just 1 hour in order to complete their irrigation cycle. And if you could stack those, then you would use less. And this is again, adding up all the sprinkler zones in the green and adding up all the drip zones, the 2 zip zones in the blue, and seeing, okay, how much time did this controller need to get that done? And we were hoping that the green would stay down here at about a little under 7 hours. And there were days when it went all the way to 12. So that would indicate that there's room for better stacking or management of getting those zones working together. And the drip zones, surprisingly, notice that the drips are showing that they irrigated far less hours than we would have anticipated. And this is again because this controller watered frequently. Little bits in only waiting 1 or 2 days before it would irrigate again on some of those. And so it didn't need to water very long. And that shows up here very quickly that, and I would see this as a problem. If you're running your drip zones only a few hours, but you're running them every 3rd day, and you've got a 20-inch root zone, then maybe that's not the way you want to do it going forward. So effective rain. Again, the solid line is the actual effective rain. The dashed lines are the optimal effective rain that could be had. The next graph is the one that I tried to allude to that was coming up. Notice that because this controller watered so frequently and maintained several zones closer to field capacity for long periods, you can see that it did not do as well on average effective rain. It only had 65% across all zones. And 3 of these really diverged away and did not look near as clean as controller number 6 did, that had 81%. So this is effective irrigation. So we've moved from rain now to irrigation. The dark solid line is the actual effective irrigation, and the dashed lighter lines are the optimal. It's really fun to see that they are close together, that the dark blue and the light blue are close together. The greens are together, the reds together, and the yellows are together. So the controller was doing its job, and you would never know or would never get concern yourself with how frequently it's watering unless you added additional evaluation of its performance, as is done with test protocol number 2. Again, we would hope that effective irrigation would follow the optimal line. Again, we're seeing stair steps on zone number 5, but the others we're seeing tiny steps, indicative of that frequent irrigation. Zone number 1, yes, we see that the run times are decreasing as the season declines from mid-July to mid-October. That's good. But notice how frequent some of the irrigations were every day during periods of time trying to catch up and do good. Whereas we would have liked it to irrigate deeply and infrequently and much fewer irrigations and the potential to conserve more water. So that's zones 1 and 2. Let's go to 3 and 4. Again, we're seeing very frequent irrigations. We're seeing declining amounts of irrigation, whereas if we were watering deeply and frequently, we would have the optimal controller is timing those to refill the available moisture reservoir as is needed. And this controller was not able to do that because of the constraints it had. 5 and 6. This is interesting. Again, we see very frequent irrigations on zone 6. Number 5, not so much, but what the good thing we see is that there's definitely decline over the 3 months, those 90 days, of reducing watering to meet the actual needs of the landscape. So this is what we want to see a smart controller do. And for many landscapes, though, there would be need to avoid watering every day for long periods of time. Daily irrigation and rain. Notice that we had one big rain event here. You see all these light irrigations happening and then one big rain event, and you can see that a whole lot of that rain was ineffective. It's all the dark green, means that it was not captured in the root zone because it was already full. So we don't want to see dark blues. There's very little there, a little more here, but there is some pink that goes with that dark blue, and there's definitely some loss of effective rain there. Again, this is zones 3 and 4, the same highlights. We don't want to see the dark blue and the pink. We don't want to see the dark green and loss of rain out of the root zone, but we do see those declines happening over the 90-day period. 5 and 6, here we see more pink. And in fact, some of these very frequent irrigations, you can see that there was no effective irrigation during that time. They simply didn't shut off for the rain. The little bit of rain was there and the decrease in FNCT. And so, but overall, it did a pretty good job. As we look at the moisture balances, I think this is telling, and you can see that when you water deeply, when you water frequently, we've seen this before, that controllers tend to slowly get off either one way or the other. This one is because rains came and helped pull it up right there, but it tends to hover, like on zone 2, it tends to hover right at the field capacity level, which means there's limited opportunity to capture rainfall. And whereas if it was watering deeply and infrequently, there it would overcome those issues. Again, staying up high near the field capacity, staying up high, but this is starting to see some good cycling happening. Some dry down and covering like that. So there's 3 and 4, and this is 5 and 6. And surprisingly, zone 5 did start to track, except for a period here where there's quite a bit of rain. It stayed up high, and then it would dry down slowly, and then it would catch up. There again. So Irrigation adequacy and scheduling efficiency. Controllers 6 and 14 had nearly identical high ratings for their average of those adequacy and efficiency. So if the owner or manager of the property is comfortable with Wi-Fi connectivity and is in programming monitoring with the app on a smart device, then the make and model of controller number 6 could be a good choice. However, if the owner operator is most comfortable with programming being the controller faceplate, turning dials and pushing buttons, and prefers use of on-site weather sensors at his specific property, then the make and model of controller 14 could be a preferred choice. Both are similar in cost. However, if the owner manager favors low water use plantings, then the capability of controller number 6 could make the difference because it has the capability of irrigation day intervals and specifying those. Frequency would be more, irrigation frequency would be more complementary towards maintaining plant health and vigor over the long term. Now, we've been drowning in data, but we are nearly done. The relative cost of controllers. Now, 2 of the controllers were over $1,000, but the majority of the controllers were in the, let's say $200 to $300 range. So it's a good testing controller does not have to be also be a high cost controller. But there may be other reasons why controllers are selected than just on the comparison of test results. It is notable that 7 of the 10 controllers tested were below $400. 3 were below $200. And the individual good performers that I've highlighted, number 6 and number 14, and were utilized in the presentation are included in controller ID C and controller ID E. So there's where our 2 high performers came from. Is there still room for improvement? Yes. Significant advancements in improved irrigation scheduling management have made, particularly in the area of smart controllers. Numerous models and options are readily available. Determining which will adequately meet the needs and properly support the objectives for any given landscape, it can be a daunting undertaking. But proposed testing protocol number 2 has good potential to impact irrigation industry for the better by providing better data in a way that decisions can be made appropriate for any given application. One of the things I want to point out is that I mentioned that some of the wireless sensor controllers may have had problems with connectivity to those sensors. And what happens is the manufacturer specifications for maximum line of sight, their sensors range from 800 feet to 1,500 feet. We had 1 of the 4 that performed well, and we're not sure why the other 3 didn't, but they were all under 800 feet, but they were, controllers were inside a metal building, and that's always problematic, and there just weren't resources to overcome that in the limited time frame we had. But that's a good thing to keep in mind with using wireless sensors. Now, moving forward, ASABE X627 does not establish performance standards for smart weather-based controllers. It just says how to do proper testing. If entities are interested in the benefits of alternative protocol number 2, they either can proceed independently or work collaboratively to establish performance benchmarks. Benchmarks could be simply a pass-fail, or they could be comparative. And at this point, I'd like to invite Brent to add some comments. If we can get him unmuted.
Okay, now I'm unmuted. So I guess the X627 standard is in the final stages of being approved by ANSI. So within the next few weeks, that should be done. And then, you know, where to go forward. So this was a fairly expensive test to have to perform, and it probably needs to be redone with a different lab and different people to verify that they can get the same similar results, and then to try and establish that baseline. So I know with EPA WaterSense program, they established the criteria by which they did a pass-fail. So nobody actually knows how any controller performed on any particular zone. They got a label or they didn't. And so that was just a simple pass-fail, but the criteria they used is what Mark showed. And, you know, and that was strongly recommended to them by the SWAT initiative from the Irrigation Association. On this other one was for a longer period of time, and we did from midsummer into the fall. You know, it might be interesting to say, well, what happens if you start in the spring and end in the midsummer? You know, where you got rising ET versus declining ET. Well, I don't have a strong answer for what would the results be. But I think in reality that this idea of 100% perfection is not a reality, that somewhere, you know, around the 80% maybe what we would like to say is a great improvement over what is considered normal by most water utilities, especially in the West, when they're trying to size water mains and stuff. They tend to look around a 60% irrigation efficiency. And so if we can get to 80, that would be a pretty good step forward. I don't know if I'm answering that question real well, Mark, but you know, the standard is almost done. Again, it describes the test procedure, but it doesn't give any criteria on what would be a recommended acceptable performance. And I think that's where the industry will need to kind of figure that out and you know, offer some good ideas of what would be acceptable. This idea of what step number or test method number 2 is that California Energy Commission is actually going to do something about smart controllers in the near future. And when I had conversations with them, they said it's not good enough for it just to water the right amount. It has to be good enough to water at the correct time. And so they're looking at it from an energy point of view. And so a daily irrigation event to them is not as good as one that can stretch that out from an energy point of view. And so it could actually be figured out from the EPA WaterSense test that they do for 30 days, but that's not one of the criteria that's written. Yet they probably, every lab would have the data to know how frequently did a irrigation event take place. It's just not currently reported anywhere. So now I did see a question, I think, from maybe Steve Smith or something about, you know, are the manufacturers making improvements? Yes, they make improvements all the time. And I think that is one of the advantages of Wi-Fi controllers, is that automatically they will download improvements in their algorithms and stuff like that. And you may never know it, and we may never realize it. So what we were testing in 2019, if we went and bought those same controllers in 2020, I couldn't vouch that they would be really identical. There probably is a revision number, and we have no idea what improvements they're making, but I have a lot of confidence that the manufacturers are very interested in this, and as they see opportunities for improvement, they make it. And with Wi-Fi, it's seamless. It's you know, you just have no idea it's happening. If you have on-site sensors, well, then there has to be some physical changes done at the controller. And so that's the best I know, that the wireless technology, the Wi-Fi, enables manufacturers to do more without really interrupting whatever the current water manager is doing.
I think the follow-up to that question, though, Brand, I'm glad you touched on it. I was just about to ask it, but Stephen also asked in that question, do you think since this experiment has occurred that the controllers tested have updated any of these algorithms, thus, you know, changing results?
I only can guess, but I'm going to say yes, some of them probably have. You know, I know Mark has had contact with them, shared results with them. They study it, and so I can assume that there has been improvements made. And so what you would buy on the shelf today may not be exactly what's hanging on the wall at the IIC right at the moment.
Great, thank you. Mark, there is a question about a particular slide, slide 53. And in this question, it said that you referenced that a changing ET is important to chase, and the 90-day test chases the ET because ET went from pretty high to pretty low. And they comment, however, missing a quickly rising ET could result in dead plants, where missing a falling ET results in too much water but less damage to plant material. The question is, don't you think that it is just as important, if not more important, for the test to chase a rising ET?
I would agree, yes. And unfortunately, we didn't get everything up and running in 2019 until the middle of the season. And so we were left with the option of doing a falling ET. And that would be, like as Brent mentioned earlier, is that would be a good thing to verify. What actually has to happen is somebody has to show interest in utilizing this test protocol and essentially fund that kind of testing to find out what's going to happen.
So I see another question from Charles Hillier about if the controller's algorithm can be updated on the fly, so to speak, shouldn't we be testing their algorithm and not the controller? I would be hard pressed to say that they would give us the algorithm.
I want to make sure that Brian Bear's question gets answered too. He says, curious to know how many of these controllers offer a tool in their software to reset individual zones back to neutral. Once they get off, then what happens?
I don't have that tallied up, but most of them have some way to kind of start over. I can think of several controllers that actually let you set what the depletion is on a given day. And so you literally can tell that this is what the depletion is. Others simply give you a high, medium, or low. And it's a little more coarse. But I would say most of them do give you a way to kind of start over. The two that do a weekly watering schedule probably don't need to even have that kind of capability, because if they're a little bit behind, you can just manually say, well, I'm going to have it water 15 minutes, and then I know that it'll be at capacity and it'll start from there. So, but yes, that would be something that could have been added to our summary results.
So if I could just throw in a kind of an observation, a lot of these controllers have really advanced features, and yet when I work with contractors, they're barely capable of really understanding the basic features. And so they miss the opportunity to take advantage of a lot of the features the controllers have built into them to do, like the frequency, the cycle and soak and stuff, because it's just such a different way of programming that they just don't take advantage of it. And we all know nobody reads instructions. You have to go online if you want to learn any of this stuff, and to be pressed for time. And so if it's not really super intuitive, then it's really hard to get them to take advantage of that. And that seems to be more true with controllers that have on-site sensors than the Wi-Fi, which gives you a something you can do with your smartphone or something that will maybe lead you that way. So I see that as an opportunity just to get people to understand the smart features that controllers offer, and then really have confidence that they work.
I would second that contractors typically, relatively few are actually involved in the day-to-day irrigation management. Most come and go, and they don't want to have a callback because that's not revenue for the business. But what's interesting is that I would say that there were 4 different controller makes and models that performed well. And that was gratifying to see that there are controllers that can take on this kind of a more rigorous test and actually show their stuff. couple of those were fairly complex, but to me, the menus were intuitive and you could walk through it without having to resort. Not everybody's there, but one of them was extremely simple. And it was surprising how simple the programming was and how well the results were with basically no brain drain at all.
Another question that just came up was what time or what testing time period is the ANSI standard currently using?
So there is not a current ANSI standard for testing of smart controllers. What is in the marketplace and has been very well accepted is the EPA WaterSense program has essentially taken the SWAT testing protocol that we developed in 2008. And basically they went through public comment period, et cetera. They made 3, adjustments to that testing protocol that SWAT had, most of which I thought was really good. I still have heartburn over one, and they know that they would count irrigation before rainfall when figuring out the soil moisture balance. So no controller was ever penalized because it irrigated on the same day that it rained. In the SWAT protocol, we counted rainfall first, taking advantage of Mother Nature, then irrigation. And that's what kind of led to this idea of maybe doing an hourly calculation, because if a controller was scheduled to water at 5 o'clock in the morning, and it did, but it rained at 11 o'clock that night, the way we were calculating it, then the controller was penalized for irrigating exactly when it was scheduled and should have, but a late night rainfall event would penalize it. So the hourly calculation was one of the ways that we tried to overcome that and counting rainfall first and then irrigation. And that's how that irrigation efficiency and the rainfall efficiency was being looked at. So the ANSI standard probably will be actually published at the end of the month. EPA WaterSense program was very involved in the development of the standard. They're actually looking forward to it because when they are forced to go through their testing protocols, et cetera, then they can point to an ANSI standard and saying, this is what we are following. There is no conflict between the standard and what they're currently doing. But this is, 10 years later, and so it works well for them. I see that Teague has got a question that everybody wants, and that is, they want the Mark to reveal his code for IDs and stuff. And the intent is we were never going to do that is a blind test, so to speak, because what we're trying to do is validate the testing protocol, not looking to say this is the best controller out in the marketplace. Eventually that will probably happen, but the intent was just to validate this test procedure and verify that it does work, and it's now going to be in the marketplace.
I would emphasize too that test protocol number 1 is still a daily balance calculation. Yeah. Test protocol number 2 is the hourly soil moisture balance calculation.
So AJ, I think we've used up our hour.
Yeah.
That's perfect. I was just about to call it. So I appreciate everybody staying on a little past just so that we could answer some of these questions. And once again, I'd like to thank both Brent and Mark for joining us today, and Susie for being our moderator. Thank you so much for everyone joining us. And have a great day. We will put this recording on the IIC's YouTube page as well, so that we can have it as reference material for anyone who wants it. So thank you for joining. Have a great day, everyone.
Thank you.
Thanks.